In this video, we're going to discuss ions and the quantum mechanical description. So the quantum mechanical description specifically of ions. If we looked at Na on the periodic table, Na is an alkali metal with 11 protons and 11 electrons. Because Na is in column 1A, we know that it has one valence electron that it's trying to lose. It's a metal atom that's trying to lose one valence electron. So we know that Na Na will try to turn into Na with a plus by giving away one electron. It loses one electron. If I asked for the quantum mechanical configuration of Na+, we would walk through the periodic table, and Na is going to be 1s2, 2s2, 2p6, 3s1. And the reason it finishes at 3s1 is Na is in energy level or principal quantum number 3, sub-level S, and it's the first one over. So if we were to draw the orbital notation, we would have an up and a down in the S. We would have an up and a down in the S. The P has 3 orbitals, the X, the Y, and the Z, and we'd have an up and an up and an up and a down and a down and a down, and then the S would have an up. This is, and the last electron would be a 3s, it would be a 3s up electron. 3s up electron. This is all the atom of Na, the Na atom. But we know that Na has a desire to lose this one valence electron. We know that it wants to lose this one valence electron because on the outside there is only one electron. And if it loses this one valence electron, then it'll have 6 electrons in the 2p, 2 electrons in the 2s, and so on the outside, it will now have 8 valence electrons if it can lose this one electron and turn in from an Na into an Na plus ion. So this is Na. So if I asked you about Na plus ion, we know that Na plus ion would be a 1s2, 2s2, and 2p6. This Na plus will not contain this last electron because it changed from an Na to an Na plus. So the orbital notation would be an up and a down for the S, and for the 2s, an up and a down. And then the 2p, x, y, and z would be an up, an up, an up, a down, a down, a down. And then the last electron for, remember we are looking at an ion of Na plus. In looking at that ion of Na plus, the last electron is the 2pz down. So notice Na still has, well, it always will have 11 protons, and Na plus will always also have 11 protons. This atom of Na has 11 electrons, but this ion of Na only has 10 electrons. It turned into a positive ion. Now, when we look at this structure, it's very important to point out the outside, the inside still has 11 protons for Na+, but take a look at the outside. The outside of Na+ looks exactly like which atom? Well, if we go to the periodic table, and we know we have 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6. The 2p6 looks like Ne. So the outside of Na plus is equivalent to Ne. Why does Na try to turn himself into on the outside looking like Ne? What is the purpose of that? That's because Ne is has a full outer energy level. Ne is a noble gas. So Na is trying to make himself look just like Ne on the outside. So what does it do? It loses its valence electron to turn into an Na plus, so that on the outside it's equivalent to the nearest noble gas. Because metals want to lose electrons, it loses one electron, and now on the outside it looks like Ne. So we could say, I'm going to use this, not equal, but equivalent to Ne. They're not the same because Na has 11 protons and Ne only has 10 protons. So these two are not equivalent. They're not equal, but they are equivalent on the outside. Let's take a look at another example. In the second example, let's take a look at sulfur. Sulfur, we know, will want to change from an atom of sulfur into an ion, and because it's in column 6A, it's going to want to gain 2 electrons to turn into an S with a 2 minus. It wants to gain 2 electrons. So if we walk through the periodic table in order to get to sulfur, you can see in the third principal quantum number, it's already got its 2s filled, and then it has 1, 2, 3, 4 over in the P. So for sulfur, the atom of sulfur, it's 1s2, the quantum mechanical description, 2s2, 2p6, 3s2, and then 3p4. It's principal quantum 3, 3s2, 3p, 1, 2, 3, 4. 3p, 4. So the s orbital has an up and a down. The s orbital has an up and a down. The p, the x, y, z, has an up, 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 down, down, down. The s has an up and a down. And then the p, x, y, z, has an up, an up, an up, and then a down. So the last electron for the atom of sulfur is the 3p x down electron. This is the atom of sulfur. The atom of sulfur, because it's number 16 on the periodic table, it has 16 protons and 16 electrons. The atom of sulfur is neutral. That means it has the same number of positives, same number of negatives. But it's not stable. The reason it's not stable is it wants to change itself. What does it want to change itself to? It wants to add a down electron in the 3py and a down electron in the 3pz. If right now you look at the last energy level, the last energy level is energy level 3, or principal quantum number 3, and you can see it has 2 electrons here, 4 electrons here, which only give it 6 valence electrons. That's why it's sitting in column 6A. It wants to gain 2 electrons so that it can have a full outer principal quantum number with 8 valence electrons. So now let's take a look. If sulfur turned into an ion, we would have 1s2, 2s2, 2p6, 3s2, and 3p6. 3p6 because it's going to add 2 electrons. Remember, we're going to be putting here the ion of sulfur, S with a 2 minus, which will still have 16 protons, but now it will have 18 total electrons because we are adding in 2 electrons into that 3p. So we have an orbital, 1 orbital for the S's, 3 orbitals for the P's. The P's have an X, Y, and Z designation for the orbitals. Here we have an up and a down. Here we have an up and a down. Here we have an up and an up and an up and a down and a down and a down. Here we have an up and a down. And now notice there was a change. We don't have 16 electrons anymore. We gained 2 electrons. In the first unit, we just memorized that 6A, we were gaining 2 electrons to get to 8. Now we have a clear understanding of why that happens, because the atom of sulfur has a half-empty 3py and a half-empty 3pz. It wants to gain 2 electrons to become a 2 minus. So now, at the third principal quantum number, it's got 2 electrons there, 6 electrons there, and now it has 8 valence electrons. So it changed from 6 to 8 valence electrons. Now, on the outside, the last electron now, the last electron for the ion of sulfur is the 3pz down. 3pz down. The outside of S2 minus is equivalent S2. Well, let's look. What does the outside of S2 minus look like? Well, S is here with 16 protons, 16 electrons. It's trying to gain 2 electrons. When it gains 2 electrons, it now has 18 electrons. So the last electron is a 3pz down. It finishes with 3p6. 3, we're here. And then p6 is argon. So the outside of S2 minus is equivalent to argon. Why does it want to do that? It wants to do that because argon has a full outer energy level. Argon is a noble gas. On the outside, argon is full. And now S2 minus is equivalent to. The outside of S2 minus is equivalent to argon. So now the outside of S2 minus is equivalent to argon. So now argon has a full outer energy level. So S2 minus has a full outer energy level. S2 minus has a full outer energy level, just like argon. I'm going to slide back to here, and I'm going to put Na plus also has a full outer energy level, just like neon. So the quantum mechanical description of sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. The quantum mechanical description of the sulfide ion, the S2 minus, 1s2, 2s2, 2p6, 3s2, 3p6. The outside is full. The quantum mechanical description of sodium, Na, as an atom, 1s2, 2s2, 2p6, 3s1. But the quantum mechanical description of the sodium ion, the Na+, 1s2, 2s2, 2p6. I hope this helps in understanding the quantum mechanical description of ions.